All right. Welcome back. This is now we're going to start with chapter six. Chapter six, in this course, we will be talking now about another new concept. We call it a level of service. A level of service is more or less like a grading system. How good is that roadway that you're driving on? We're going to study again what's the level of service or LOS for freeways, for highways, and for multi-lane highways, and also just two-lane highways. So let's get going here. So the very first lecture here, we're gonna be defining what is the level of service and how can we compute the level of service for freeways. So a freeway, again, we typically use the word freeway and a highway in multiple occasions, and sometimes we mix them up. But this is the time now where we need to define that, technically speaking, there is a difference between a freeway and a highway. Freeway, again, may be defined as it's a divided highway with a full control of access and two or more lanes for exclusive use of traffic in each direction. Basically, a freeway is, as I just again, this is the official definition, is basically a way, at least we have two lanes per direction, and we have full control of access. That means, again, we can control who is entering the highway or who is entering the freeway. It's not like being in the city and you can just enter this roadway at any point, at any given point. Now, no, it's controlled by having on and off ramps. These are the only places that we know, and we control the entrances or the exits of traffic flow into that facility. And again, we have to have minimum of two lanes per direction. And by definition, freeways, therefore, will provide actually an uninterrupted flow. We mentioned this definition before. Uninterrupted flow on freeways, that means there is no signalized or stop controlled at grade intersections. And again, direct access to or from the highway are, again, they are known, and they are um, very limited. Sometimes, again, once per mile or once per couple miles, especially if you're in a rural setting. The access to and from the freeway is limited to the ramp locations, which I just mentioned, and as well as the opposing directions of flow are continuously separated by either a raised barrier or at grade median or a raised traffic island. So if you are driving on that freeway, you are actually do not care by any means what's going on the other side. There is a big physical barrier between the opposite directions, and that's how we define a freeway. So operating conditions on freeways are actually dependent heavily on characteristics of the roadway as well as the interactions between the vehicles within the traffic. It doesn't depend on the traffic control. There is no traffic signs, there is, traffic signals, there is no stop signs, there is no yield signs. The main operations and the quality of the operation on freeways highly depend again on the characteristics of the roadway itself, how good the roadway it is, and also the interaction between the vehicles on that freeway. So operations can be affected when we're talking about, speaking of operations, can be affected, of course, by environmental conditions. Again, if it's an icy condition, snowy condition, rainy condition, windy condition, that also can make a big impact on operations, such as, again, weather or even, again, lighting conditions. Sometimes, again, driving at night on a freeway, your experience on that freeway is going to differ if there's enough lighting or not. And therefore, the level of service eventually on this freeway will change and will be highly affected by changing the lighting conditions. Also, pavement conditions, the pavement itself, the surface. Is that surface of the pavement, is it a rough surface or a smooth? If there is lots of cracks, lots of rutting, lots of distresses, that's also is going to affect, again, what's the level of service on this freeway. And of course, the occurrence of traffic accidents, or to be more generalized, in any incident that happens. If we have lots of incidents that happens on this segment, known to be, highly dangerous, then the level of service also will go down. So speaking of a freeway, any freeway actually consists of three component parts. So the first part is what we're going to call the basic freeway segment, and then we're going to have weaving areas, and then we have the merge or diverge areas. To get to the definitions, I like to point out here. So the basic freeway, this picture is actually give you an idea. Where is that basic freeway segment? The basic freeway segment is actually the area in green here, where this is just a long stretch on in that freeway that it doesn't include any on and off ramps or any weaving areas like what you see here. It's just again that long stretch, easy enough. Sometimes it's actually boring, but that's the most safest location. And again, it's just continuous stretch. There's no interruptions, except again if there is an incident that happens. So this is the basic freeway segment. And again, by definition, those segments again of the freeway that are outside the influence area of ramps as well as waving areas. The weaving areas, these are now the segments of the freeways where again two or more vehicles flows must cross each other path along again the length of that freeway. While so this is again the weaving areas, they are usually again formed on ramp that is followed by an off ramp. If the on and off ramp they are very close, you're gonna see now that there are some vehicles trying to enter trying to exit the highway versus again others are trying again to speed up to enter the highway. So again, we're gonna have now a conflict of interest where people are trying to get into. Some of them are trying to get in, and some of them are trying to get out. And that is one of the most dangerous locations in any freeway, where the merge or diverge. These are the points at which on and off ramps join the freeway. So those are again the three major segments of any freeway. And again, you may agree or disagree, but to be fair, determining the level of service for any freeway and to be fair, comparing different freeways, we tend actually to pick the basic freeway segment to judge what is the true level of service for this freeway. So a basic freeway segment is typically again characterized by three main performance measures. So once we pick that basic freeway segment, we actually now look into some of the major performance measures that define for me what is the level of service for this freeway. One of them is again the density, and we defined those on the previous chapter. Density again in terms of passenger cars per mile per lane, and then also the speed, which is in terms of mean passenger car speed, as well as the volume to capacity ratio. Volume to capacity ratio, this is similar to again how far are we from the ultimate strength of a steel sample, for example. The volume, this is actually the actual traffic flow, whereas the capacity, this is the ultimate traffic capacity or the ultimate traffic flow possible. So let's start again from the very beginning. Density. If I have again, if I'm driving on a roadway or if I'm driving on a freeway rather, that the density is high, the level of service will go down. If the density is low, that means there's not much passenger cars per mile per lane. The level of service, your experience as a driver is gonna be way better. Speed also. If your speed, and we're gonna define, there's something called again FFS, free flow speed. If your free flow speed is high, that means the level of service will go high, A or a B. But if the free flow speed is significantly low, because if it's affected by other factors, then the level of service, your rideability or the ride quality on the freeway will be low. Same thing with the third item, which is volume to capacity ratio. If you know that you can handle, let's say, 2,000 vehicles per hour per lane, that is the capacity. And if the real volume is 1,000, then the ratio is 1,000 over 2,000. That's 50%. That's awesome. But if the actual traffic flow is actually, let's say, 1,900, now 1,900 over 2,000, that's like 0.95%, or 95%. So that's now we're reaching the ratio. So 1,000 vehicles as an actual traffic flow compared to 2,000 volume, then this is actually going to tell me that the level of service is really high. While if I have 1900s versus 2000, the ultimate, this is the level of service is going to be really, really low. So again, the higher the density, the lower the level of service. The higher the speed, so let me draw this here for you. So the higher the density, the level of service will be low. The speed, the higher the speed, the higher the level of service, which is a good thing. And of course, the volume to the capacity ratio, if it's low, that means the level of service will be high. So those are actually the three factors in theory that they are going to affect the level of service calculations that we're going to go through today in this lecture. So let's get into some more details on how can we get, again, that actual level of service for any freeway that we're interested to analyze. Again, this is a note of, again, explaining on more details, like what I'm telling you. Again, each one of these measures are an indication on how well or how poorly the traffic flow is being again accommodated by the freeway segment. Okay, so something called um, this is now the service measure. How are we going to now measure the level of service? So although again, you may think again the speed, if the traffic speed on this freeway segment is high, then the level of service is going to be high. I would tend to agree with that. It's a major indicator for how, again, the quality of driving on this location, but also there's other factors that affect the level of service, such as, again, the freedom to maneuver within the traffic stream, and again, proximity to other vehicles are also important to be considered. So again, these other concerns are related to the density of the traffic stream. So the density, as I said, the density increases as the flow increases up to the capacity. And again, we've seen that in chapter 5, resulting in a measure of effectiveness that is sensitive to a broad range of different flows. So in a nutshell, again, this is for all of these reasons, density is the main performance measure that is used actually to define what is the level of service for that basic segment of the freeway. So really, if I have a density, which PC, this is passenger cars. If I have a density of 11 or less of passenger cars per mile per lane, the level of service will be A. The grade of this freeway is A. If I have a density somewhere between 11 and 18, which means now the density is higher, the level of service would be B. And then if I have, let's say, 35 to 40 passenger cars per mile per lane, that is level of service E. And if it's more than 45, this is actually a big troubled freeway segment, and with a level of service F, and some attention need to be drawn at this location. So now, what is the procedure that we're going to be following, the mathematical procedure to determine what is the level of service? So first, we need to establish something called base condition and capacity. What does that mean? It means that instead of going through the calculation right off the bat, we define some base conditions or some ideal conditions. If I were to find it in any freeway, the level of service is already predetermined as the level of service A, or the grade is going to be A. If not, if any of these conditions are not met, then you've got to go through now the calculations. The calculations actually include, we need to estimate as or measure the free flow speed, what I just talked to you about, FFS. We need to measure the free flow speed, and you need to measure the flow rate, or what we call the analysis flow rate. So if you get the flow and if you get the speed, you will be able now to get the density, and from there you're going to be able to determine what is the level of service. So that now pause. The next question is, what are these base conditions? What if you were to design a freeway that has a level of service A, what would you expect to see on this freeway? So the base conditions, the very first condition is we need to have a minimum lane width of 12 feet. Any lane on the freeway has to be 12 feet at least in order to consider it as level of service A. Next is the minimum right shoulder lateral clearance between the edge of the travel lane and the nearest obstacle or object influencing the traffic behavior should be at least 6 feet, which meaning again, let's now, I'm drawing one direction. I'm assuming again, there is a big barrier, physical barrier between the two directions. So I have two lanes here. And now I'm saying the first condition is I have to have minimum 12 feet here. But now between the edge of the travel lane all the way to, uh, again, the edge again, or the next obstacle, which is this is the shoulder, minimum at least 6 feet. If I have 6 feet or higher, this is awesome. This is actually, this is, I'm meeting the level of service A condition. And also again, we have to have minimum median lateral clearance of is 2 feet. But again, that's typically, again, we don't care about the median because typically the median, by definition, freeways have wide medians. So the main concentration is really, do I have a right shoulder width of a minimum of 6 feet or not? Also, I have to have traffic stream consisting of passenger cars only. I know this is too ideal, but this is how we define level of service A. If almost 100% of the vehicles driving on this freeway segment, they are only passenger cars. There is no big trucks. There is no 18-wheelers using this facility. If that's the case, then we're still continuing with the assumption that the level of service at this location is A. Next is there is no on and off ramps within 3 mile upstream or 3 mile downstream of a segment midpoint. So here what I'm saying is if we have too much on and off ramps, more than 6 total between the upstream and downstream, then we're deviating from level of service A. If we have less amount of on and off ramps, again, why is that? Because again, the lesser the ramps, that means the flow is going to be continuous. Your driving experience is going to be much better, and therefore the level of service will be A. Then we also have to have a level terrain with grades no, not greater than 2%. So again, you're not really climbing. So that means again, so going again, this is, I'm talking now about the vertical alignments. So the G, remember again when we did the crest vertical curves or sag vertical curves. So the maximum, it should be 2%, either going up or going down. If it's more than 2%, that means again your speed is gonna start now to be significantly lower just because you're climbing, and therefore the level of service is gonna deviate again from level of service A. Next is driver population dominated by familiar users of the roadway. That means, again, you're hoping that 95% of the drivers on that freeway, they are using it on a daily basis and they are fully aware of it. They are fully aware of any horizontal or vertical alignment changes, and therefore um, they are not gonna like have a drop in their speed significantly at certain point, and therefore it may affect the level of service. However, if on the other extreme case, if let's say if this freeway leads to a national park that is again 50% or more of the people using that freeway, this is their first time using the freeway, and therefore they are more curious, if again, and they are more cautious. They don't know again the bends of the roadway, if you will, and therefore their speed is going to be lower, and therefore you would expect that the level of service would be lower just by the fact that there is lots of visitors using this freeway for the first time, and therefore um, this is gonna lower their speed, and therefore the level of service will be low. So really, in theory, again, if you satisfy all these conditions, meaning that I have to have wide lanes, at least 12 feet, I have to have a wide shoulder, minimum 6 feet, I have to have the traffic is only about passenger cars, no trucks lowering the overall speed of the flow. If I have low amount of on and off ramps, if the vertical alignments are maximum ups or downs, more a maximum 2%, and if most of the vehicle drivers are familiar with the roadway, then it's if I satisfy all, if you satisfy all of them, then that is will lead us to a level of service A. If you do not satisfy any of these conditions, then you have to go through the calculations, and you know that you are not going to be at level of service A. So assuming that you're not going to have level of service A, and again here this is just an idea of the lateral clearance that I was telling you about. This is here a wide lateral clearance versus here a very narrow lateral clearance. Yeah, even between the opposite directions, again this is very narrow, and also here there is a distance versus here again there is barely not much. Heavy trucks, again, this is also another factor. Again, just by looking at the picture, if I have again large gaps from in front of trucks, so these gaps typically, again, if I have a truck, people will try to avoid being close to it, and therefore that's going to lower the speed, and therefore the existence of higher percentage of vehicles um, will result again in lowering the level of service. Okay, so going back to here, we said these are the steps. First, I need to check the base condition. So let's assume you did not meet the base condition. Then now you need to go through uh, the three other steps, steps 2 and 3 and 4, to calculate the level of service. The first step is which is here number 2, is we need to estimate or measure the free flow speed. So how can we do that? Actually, this is what we're about to say. So the free flow speed. So let's first redefine it. The free flow speed, this is actually the mean speed or the average speed of the passenger cars measured under low or moderate flow rates. So I'm not, again, the interest here is if there is almost, again, no cars or very minimal amount of cars, and now the vehicle drivers, they are picking their own speed. What would be that free flow speed? So to measure it, there are two methods here that can be used to determine that, the FFS. We can do field measurements, or we can estimate it using the highway capacity manual, HCM. Please again pay attention to that. Sometimes they ask about it in second exam. What's HCM? The HCM, again, the Federal Highway Administration publication. It's called Highway Capacity Manual, that let us um, again give us the tool to estimate the free flow speed if we do not have what it takes to measure that free flow speed in the field. So how can we estimate it? Again, measuring it is easy. You're just gonna go there and measure. Again, you're gonna sit there maybe for a certain amount of time. You're gonna observe certain number of vehicles. You're gonna sum them up, divide them, and get the average speed, and that will be your free flow speed. But if you want to estimate it, this is the equation to estimate the free flow speed. It's a very theoretical equation. That's why it will be provided to you in the exam if you need it. Basically, the free flow speed here, let's take a look at how to estimate it. So the free flow speed is mainly, it's 75.4, and this is miles per hour, by the way, minus couple factors here. And we want to study these factors. The first one is FLW. This is an adjustment for lane width. So this is here now giving you an idea that once we start deviating from the base condition, if I have now a 12 feet or less than a 12 feet worth of lane width, then if that's the case, I would start now to deviate from the original free flow speed. As you could tell, all of these factors, there is a subtraction here. Why is that? Because this is actually the ideal free flow speed on any freeway is 75.4 miles per hour. But if I am now deviating by changing again the lane widths, or FLC, which is the other factor, which is now the adjustment of the right shoulder. If the right shoulder is less than 6 feet, or TRD, which has to do with the number of ramps. If the number of ramps now are more repetitive, more than 6 per mile, therefore we're gonna be continually subtracting from that 75.4 miles per hour. So let's study first the first one, FLW. FLW, again, this is the adjustment for lane width. Let's go to table 6.6.3. This is table 6.3. Very simple, and it highly depends on the average lane width. The average lane width, if it's more or equal than 12 feet, take a look at this here. Very interesting. What's the reduction? What's FLW? FLW is nothing but a reduction of the free flow speed. So if the lane width of any freeway is 12 feet or more, there is no reduction. because you are at the base condition or the ideal condition of a freeway. So that is 0. But if the average lane width is somewhere between 11 to 12, or again 11.99, then the reduction now FLW will be 1.9. Whereas if the average lane width now is somewhere between 10 and 11, the FLW will significantly go up to 6.6 miles per hour. What does that mean? That means, again, assume that, again, the FFS is equal to, again, that 75, sorry, that is 75.4 minus FLW. If I am driving on a freeway that the width is 12, then that FLW is going to be 0, and therefore there is no correction when it comes to lane width. But if that 12 feet now is becoming an 11 feet, then it's 75.4 minus 1.9. Or if the width now of a freeway is 10 feet, then the FFS is going to be 75.4 minus 6.6 miles per hour. So a huge difference and a huge jump. Just by the time you keep reducing a foot from the lane width, what's going to happen? Basically, as a driver, if you drive on a narrow roadways, what's going to happen? By your instinct, again, you're going to start reducing your speed. You're going to feel that you're not really comfortable. This is too narrow. I may actually again end up again interacting laterally by the vehicle besides me, and therefore your speed, your free flow speed will get reduced naturally. But what's interesting here that the reduction from 11 to 12 here. So if you are just reduce the lane width by 1 foot, I'm gonna reduce the free flow speed by 1.9. But if I'm reducing by 2 foot, you would think it's linear, but that's not the case. Once now it's really narrow, 10 feet instead of 12, now you're really reducing your speed by 6.6 miles per hour. All right, so we got that, the FLW. How about now the FLC? FLC, again, it has to do with the width of the shoulder. And that's why we go to table 6.4 instead of 6.3. 6.4, here we go. We have now 6.4 is the first thing to get into the table is what is the right shoulder lateral clearance? What's the width of the right shoulder? And then the other factor here that's going to get us to one of these 4 columns is the lanes, how many lanes in one direction. So here, a big factor here also is the how many lanes per direction. If I have, so let's first of all, again, let's see here. If I have a shoulder or a lateral clearance from the right side at 6 feet, regardless of how many lanes per direction, if I have 6 feet, that's actually a good width on the right side of the freeway. That's going to give the comfort to drivers to drive at their free flow speed, and therefore the free flow speed will not be affected by that width if it's 6 feet or more. Therefore, the FLC will be equal to 0 in this case. But what happens now if the shoulder or the lateral clearance on the right shoulder start to be lower and lower? Let's say now instead of 6, I only have 3 feet. 3 feet, if I only have 3 feet on the right side of the freeway as a shoulder, the free flow speed will get reduced by 1.8 miles per hour if I only have 2 lanes per direction. If I have 2 lanes and I only have here 3 feet worth of a shoulder, then my speed is the free flow speed is going to be reduced by 1.8 miles per hour. But if I have, how about if I have 3 lanes or 4 lanes or even 5 lanes? If I have 5 lanes, so now instead of 2 lanes, I have now again 1, 2, 3, 4, and 5. 1, 2. So now I have 5 lanes per direction, and I have the same 3 feet shoulder here. The reduction will be less because now there is lots of lanes and much less population of the drivers are going to be affected by that narrow shoulder, and therefore the reduction is going to be barely 0.3 instead of 1.8. What happens now, the worst case scenario, as you could tell, is actually to have 0 lateral clearance, which is 0, and having 2 lanes only. 2 lanes only. That's going to have the highest reduction in free flow speed of 3.6 miles, while it's not as bad if I have zero lateral clearance, but if I have 5 lanes or more on each direction, the reduction will be only 0.6 miles. All right, so now we got the FLW, we got the FLC. The last thing is the TRD. How am I going to calculate that TRD and then raise it to the power 0.84 times 3.22? The equation is very simple. It's actually, the TRD is the number of on and off ramps, 3 mile upstream and 3 mile downstream of a segment midpoint divided by 6 miles. So really the TRD is the number of miles over 6. Once you have that, you plug it into the equation and you get the FFC. So now again, we know how to get FFC. So FFC is 75.4 miles per hour minus FLW from table 6.3 minus FLC from table 6.4 minus 3.22 times the TRD, which is number of ramps over 6 to the power 0.84. All right, so going back to the steps one more time. I got that. I got the FFS as a second step. Now I need to get the analysis flow rate. What is the flow? If I get the speed and the flow, what can we get? We can get the density. And again, the density, we can use that little table or another graph that I'm going to show you towards the end of the lecture. So next step now, we need to get the flow, the analysis flow rate. Analysis flow rate is actually, we can calculate the analysis flow rate using this equation right here. So VP, that's actually the 15-minute passenger car equivalent flow rate, which is passenger cars per hour per lane. But the worst 15 minutes. I'm interested now to get the flow and now to get the worst. That's the the 15-minute passenger car equivalent flow rate. How can we get this? We get it by capital V. That's the volume, the hourly volume. And we're gonna get to learn this more in the next semester class, which is 4351. We're gonna get even to measure it in the field. The hourly volume, the volume is actually go to the field and stay there for an hour, having a micro tally or an equipment or a camera, and we measure how much the volume, how much vehicles per hour that went through a certain point. That's the V. Then the N, this is the number of lanes per direction. And by the way, I didn't mention it earlier, but the level of service for freeways is actually calculated per direction. You may have a highway, you may have a freeway that has, again, a northbound or a southbound or an eastbound and a westbound, and the level of service can be totally different. So again, for example, if I live in Tyler, Texas, and I want to travel to Dallas, Texas, and I'll be driving on I-20. That I-20, again, it has two directions. Again, going from Tyler to Texas, I may have a level of service B, while going from Dallas to Tyler, I may have another level of service B or a C. So that's why here the number of N, this is the number of lanes per direction. Level of service for freeways is always going to be one level of service per direction. Whereas again, for the next couple lectures where we talk about the 2-lane highways, it's just one level of service because there is lots of interaction between the two directions because there is not much of a median. So the experience of a driver on one direction is going to be highly affected by the other direction. But here, the N is the number of lanes per direction. FHV, this is the heavy vehicle adjustment factor. As I told you, again, one of the conditions of having a level of service A, the base conditions is to have 0 trucks. But if I have trucks, then that's why I'm going through the calculation, and having trucks is going to affect overall the 15-minute passenger car equivalent flow rate. And then FP, this is the other deviation from the base condition, which is the driver population factor. Right. So again, how popular the drivers to this, or how comfortable the drivers and how aware of them to this freeway. Again, if the majority are popular, then again, this FP is going to approach 1. If not, we're going to lower that value. Times PHF, the peak hour factor. That is a new concept for every one of you here to introduce. The peak hour factor. I'm interested to get the peak hour factor. What is the peak hour factor? Is actually a number that can tell us within the worst peak hour of the day, how bad is that hour? Do we see, in other words, let me draw this for you here. So let's talk first about the concept of peak hour. Peak hour, for example, in the city of Tyler, we have three typical peak hours. We have one in the morning, a small peak in the lunch hour, and another big one at the PM peak hour. The AM peak hour happens from typically from 7:30 till 8:30 in the morning. And again, this is time, and this is really again volume. And then the other peak, it's again somewhere between 11:30 till 12:30, and the PM peak hour is from 4:30 till 5:30. It can deviate again plus or minus 15 minutes or to 30 minutes, but those are actually the peak hours. The peak hour factor, the peak hour factor is actually, now we know that this hour is really bad. I get it. But now we want to know, using this factor, is the traffic within this hour, is it really bad? Is the traffic uniform within this peak hour, or I really have a bad 15 minutes within this hour, which is again more problematic. So that's what lead us to the definition of this factor. The peak hour factor is actually the volume, the hourly volume. This is the hourly volume over V15 times 4. V15, this is the maximum 15-minute volume within the hour of analysis. Within the hour of analysis, we pick the worst 15 minutes. So let me give you a small example here so you understand what can be a high peak hour factor and what can be a low peak hour factor, and which one we would desire to have on our facilities. So if I have the following, if I have this is the time, and typically again when we go and do the hourly volume, we measure the amount of traffic every 15 minutes. So the time, and this is the volume in that 15 minutes. So let's say from 7:30 till 7:45, and then 7:45 till 8, and then from 8 till 8:15, and from 8:15 till 8:30. One of the best case condition is actually, let's say I observe 250 vehicles in the first 15 minutes, 250 vehicles in the second 15 minutes, 250 and 250. Every 15 minutes is exactly the same. So if I look into this now, I'm trying to calculate the peak hour factor. The peak hour factor in this case would be, peak hour factor is going to be equal to the total volume of that hour, which is 1,000. So that's 1,000. That's actually, this is the capital V over V15. V15 is the worst 15 minutes or the maximum 15 minutes. Any of them is the same, which is V15 in this case is going to be 250. So 250 times 4. Why 4? Because we have 4 quarters. 4 is the number of 15 minutes periods in an hour. And that would lead us to 1,000 over 1,000. That is 1. That's one extreme condition, which is actually, this is a good condition. Peak hour factor of a 1. This is a very ideal condition, meaning that, yes, I know it's a bad hour, but within that bad hour, the traffic is just uniform. There is no really bad 15-minute and the others are not too bad. It's just, again, it's just uniform, and the traffic, that volume of 1,000, which is high, I get it, but it's uniformly distributed within these 4 quarters of the hour. The worst case scenario is actually if I have a volume of 1,000, and then from 7:30 to 7:45, 1,000, and then I have a 0, a 0, a 0. So what's the capital V in this case? It's still 1,000. So really now, going to here, the peak hour factor in this case, the capital V is still 1,000. Again, the total number of vehicles is 1,000 over, what's the V15? V15, the worst 15 minutes is 1,000. So 1,000 times 4, this is going to lead me to 0.25. This is the lowest possible peak hour factor you can have. and that's the worst case scenario. To have a peak hour factor approaching 0.25, that means again there is really a bad signalization, a bad planning, that within that bad hour, it's actually 15 minutes is the worst in that hour. So a peak hour factor of 1, that's the best case scenario. A peak hour factor of 0.25, that is the worst case scenario. This is really, again, this is bad, and this is really good. Typically, in the past 7 years or so, again, in CNG 4351, we measured the peak hour factor in a couple roadways here in Tyler, and it's about actually 0.85, which is, again, approaching a very good condition. So thankfully, we're not, again, we're not close to a bad condition where it's 0.25 or even 0.5. It's actually in the higher range where it, and again, what does that mean, 0.85 or 0.87? That means, again, the traffic within that peak hour is almost uniform. Is almost uniform. All right. So if I get the peak hour factor, again, if I get the peak hour factor, I can get now the VP. But before we do that, so capital V, again, we get it. That's the total volume. Peak hour factor, we can get to know now how to measure it, and number of trucks or number of lanes per direction. How about FHV? FHV, there is actually an equation for it. Simple one. Don't get scared about it. It's a very simple one. So FHV is now using this equation, which will be provided to you in an exam if needed. FHV is equal to 1 over 1 plus PT times ET minus 1 plus PR times ER minus 1. What's that? So FHV, again, we know that's a heavy vehicle adjustment factor, meaning that if I have a big percentage of heavy vehicles and on this freeway, I need to adjust that factor to get, because this is what's gonna feed me to feed the VP, which is the maximum 15-minute passenger car equivalent flow rate. I need to convert everything to passenger cars. That's why, again, I have to have the FHV to convert all the trucks, regardless if they are 5% of the flow or 10% of the flow. We're going to get to see, again, what's the impact of that. So PT, this is the proportion trucks and buses in the traffic stream. Is it 5%? Is it 10%? Is it 30%? And again, we typically sum up the trucks and buses under the PT. And then the PR, so the PT is here. The PR is actually the proportion of recreational vehicles in the traffic stream. So if I have RVs, again, it has its own little portion of that equation. And then ET and ER, we get these from tables. ET, again, this is the passenger car equivalency for trucks and buses, which we get it again from tables 6.5 or 6.6 or 6.8. Or, we also, the ER, we get the ER from the passenger car equivalency for recreational vehicles, and that is from table 6.5 and or 6.7. So let's get to those tables and see how do they look like. So the PT and PR, for now, they're going to be given to you in an exam or a homework. The percentage, what's the percentage of trucks and buses, or what's the percentage of RVs? What you need to obtain from the tables is the ET and the ER. So this is here the table to get the ET and ER. Again, a simple table, and most of the time we're going to end up using table 6.5 more than anything else. So the ET, which is a factor for trucks and buses, it all depends on the type of terrain. Is it a level terrain or rolling terrain or mountainous terrain? And here are, again, the definitions here. I'm going to leave those definitions for you, but really it depends on, again, how is the vertical alignments on this location. If it's less than 2%, that's a level terrain. If it's a rolling terrain, that means, again, any combination of grades or horizontal vertical alignments that causes heavy vehicles to reduce their speed substantially. Or mountainous, again, this is any combination of same grades, horizontal vertical alignments that causes heavy vehicles to operate at crawl speed. So these are, again, the three different definitions from the HCM. So why it differs, again, from 1.5 to 2.5 to 4.5, the truck factor keep increasing if I am going now through a mountainous terrain. Because imagine I have high percentage of existence of trucks and buses, and you're also driving on a mountainous terrain. What's gonna happen to the level of service? It's gonna plummet. Versus if it's a level terrain, the factor is lower, 1.5 and 2.5. The rolling terrain is somewhere in between. For ER, the same thing, which is for RVs, it's 1.2 for level terrain, 2.0 for the rolling terrain, and 4.0 for mountainous terrain. So once I get the ET and ER, I go back to the equation for the FHV, get the FHV. Once I have the FHV, I feed it back to this equation one more time. I get now the FHV. I know the V, I know the N, I know the peak hour factor. The last thing remaining is the FP. So there is another table. This is here. It's a detailed one in case if there is more analysis into this location. We're not just interested to say if it's a level terrain or a rolling terrain. I'm interested now if you are given the grade, what's the specific grade of this location, and what's the length of that segment of that highway. I'll be able to get now the ET, the specific ET depending on the grade and depending on the length of the highway. So you go here and you'll be able again to pick based on the percentage of trucks. You'll be able to pick again what's the ET in specific. Same thing, table 6.7 for ER. If I tell you again what's the upgrade, what's the maximum G, the elevation, I mean the G. If it's more than 5, again the number is going to be always high, and again depend on the length of that location. Again, if the length of that upstream location is barely 0.25 miles out of maybe a 2-mile stretch, of course again the impact will be much lower than if I have more than half a mile with high grades. Then the factor is going to increase, of course. Table 6.8 also, again, this is for trucks and buses and specific downgrades. Now it's not upgrades, it's actually downgrades, because downgrades also can also be a very dangerous situation if the downgrade is more than 6%, for example, and the trucks are just going to be rolling down in a very high speed. That also can create a dangerous situation, and the vehicle drivers are going to slow their speed, and they're going to be cautious because again of the downgrade, and that also lowered the level of service. And that's why you see that the factors are going to be way higher if it's more than 6% downgrade compared to if it's less than 4%. Leading us now to the very last factor, which is the FP. FP, this is the driver population factor. The driver population factor, again, the values of the FP, it ranges from 1 to 0.85. 1 in general, again, the analysis where you would select the FP equal to 1 if I didn't give you any details. If there is lots of again, if there is no percentage of unfamiliar drivers, you're going to assume it's 1, unless if I tell you again there is a sufficient evidence, or it is again the analyst's judgment that there is a lesser value reflecting more recreational traffic characteristics should be applied, then we can go to maybe 0.9, 0.85. The lowest is 0.85. So again, depending on the decision of the engineer, it can be again 0.95 or 0.9 or 0.85. Those are the numbers. All right, so once we have the FP, again back to here, I have now, if I have the FP, I have the FHV, I have the N, I have the peak hour factor, I have the total volume, so I get the VP. What's the VP and why do I need it? Let's go all the way back. The VP, again, I need it in the third stage. I need to get the flow. And if I know the flow and I know the free flow speed, if I know the speed and the flow, what can I get? The density. And that's what the very last step here. So really now moving forward, as you see here, this is the density. This is the equation that we derived from the previous chapter. Density, which is passenger cars per mile per lane, is actually the flow over the speed. So if you get that, once you get now the VP over S, or the speed here, or the FFS, actually, this is the free flow speed, you'll be able to get the density. Once you get the density, You can go back to the table all the way up front, this one right here, to determine what is the level of service, or a more famous figure here that we use is right here. This is the this is again, it's figure 6.2 from and it's from the highway capacity manual exhibit 11.6. This is the basic freeway segment free flow speed curves. Basically, um, if you have, let's say if I have a flow rate of 1,000, flow rate, again, this is the VP, the one that we just talked about, which is the capital V over the peak hour factor times the N times the FHV times the FP. Once you get that, this is your x-axis. The y-axis is the FFS. So if you know the FFS and if you know the VP, let's say again, the VP is 1,000 and the free flow speed is 66, for example, right here. You're gonna draw a horizontal line right here. You're gonna go a vertical line at 1,000, and that point here is basically, again, you see now, this is the level of service B. Anything from this line to this line is a level of service B. Anything in this area from the beginning all the way to this line is level of service A, and so on and so forth. So again, this is level of service C, level of service D, level of service E. Or instead of looking again at the area, you can again divide the two together to get the density. Again, the density, if I again, if it's 1,000 over 66, so that is 1,000 over 66. So the density in this case will be equal to 15.15. Same thing. See here the numbers. So this is 11 passenger cars per mile per lane. So anything at 11 or lower is going to be level of service A. This is the line that's defining that 11 passenger cars per mile per lane or lower, that's level of service A. Anything between 11 and 18, that's level of service B, and ours was 15.15, which is again sitting at this point right here, and that's why again it's the level of service B. How about if I tell you that the flow rate is 2,000, and so the flow rate is 2,000 now, double, and the speed, the free flow speed is 60. So if it's 60, so again, I'm gonna draw a line here, horizontal line, and this is 2,000. It's gonna be right here. So it's actually between these two lines, and that is a level of service D. Or same thing if you wanna do the density calculation. So the density is equal to 2,000 over 60. So that is 2,000 over 60, that is 33.33 passenger cars per mile per lane. So again, this is 26, this is 35. So between the two, between these two lines, and this is also again, it's gonna lead us to level of service D, same thing. So this is again the most famous figure here to get the level of service for freeways. There is another table here, table 6.1, to also to give you the same thing. You can have again this is what's the criteria. Basically, again, what's the maximum density, what's the average speed, what's the maximum V over C, what's the flow rate to get us the level of service. So for example, the big first part here, this is flow FFS, free flow speed 75 miles per hour. And if you pick the numbers, again, if you know your numbers, you're going to be able to just justify if it's a level of service A or a B or a C. And if the free flow speed is 70, you're going to do it here. If the free flow speed is 65, you're going to be do it here. But how about if the free flow speed is 67? You're going to be needing to do the two calculations, and then you're going to interpolate. And that's why most of engineers like to use this graph, because this graph now is continuous readings between 0 all the way to 80, and instead of here there is a discrete numbers 75 or 70 or 65 all the way down to 55. So again, with that, we finish the first segment of this chapter, which is again, we define the level of service, and we know now how to calculate the level of service for freeways. Next time, we're going to be doing the level of service for highways, and we're going to get to learn also what is some of the major differences, technical differences between a freeway, and a highway. With that, again, I thank you so much, and we'll see you next time. Thank you.